Lab 1. Motion with constant velocity. The purpose for this lab includes exploring motion in the unique case where forces acting on the system have a net value of zero, yielding a constant motion, and practice computational modeling of physics-related concepts and comparing that with real-world demonstrations of these concepts. Today we are focusing on Newton's second law, and equivalently the momentum principle, wherein forces and therefore change in motion when the net forces and magnitude are the product of the mass and acceleration of an object. The scenario we are observing today is that of a rounded object pushed initially to a full speed of 34.7 centimeters per second during time t equals 0 to time t equals 1, then rolling at a constant speed for a remaining time of 2 seconds. When calculated for the main result of this lab, we should expect the object should cover a distance of about 68 centimeters during this time. To obtain these graphics, we coded the necessary conditions in the glow script as shown in the image. So what does the code do? From top to bottom, the program includes setting the initial position to 0, setting the initial time to t equals 1 to match the time we begin recording data in the lab, setting the change in time to 0.033 seconds to match the frame rate of the lab recording, setting the max time to 3 seconds, which is how long it takes the object to span the remaining distance, setting the net force to 0 to convey a constant mass and an acceleration of 0, setting the velocity to remain constant, updating the position by the velocity per 0.33 seconds rather than per second, and finally incrementing the time by the change in time before updating the graph. In this 2-second clip, we observe a system including a yo-yo with rounded edges, rolled to span the surface of a clear level desk length about 60 centimeters. The main physics concepts in action here include Newton's first law of inertia, where an object in motion maintains this motion unless a force acts upon it. Newton's second law, where force equals mass times acceleration, and Newton's third law, where for every action there is an equal and opposite reaction. In setting our initial conditions, we consider a few things. Before the clip, a human applied force acts on the yo-yo in the positive x direction. Accredited Newton's second law, the yo-yo accelerates in proportion to the force applied. During the clip, as shown by the figure on the right, we assume the only forces acting on the yo-yo are the gravitational weight force from the Earth and the equal and opposite force of the desk pushing back on the yo-yo, both acting in the y-axis. For the x-axis, there are no forces that we consider. Thus, we find, in practice as opposed to mathematically, that the distance traveled changes at near, however, non-constant rates. Over the remaining 2-second period, the yo-yo travels a total of 68 centimeters. Using the theoretical model with a net force of 0 and a constant mass, using Newton's second law, we know that the object should not accelerate. As a result, we predict that since the object travels with its initial speed of 34.07 centimeters per second, after 2 seconds it should travel a distance of 68.14 centimeters, which is depicted in the graph. In the practical model, since we use this final distance and time to determine the constant velocity, we confirm that the yo-yo travels the predicted distance in the same time frame. However, we see in the graph that it is not covered with a constant speed. This could be due to multiple factors. One of these includes friction on the yo-yo creating a force in the negative x direction, causing a negative acceleration to slow it down. Another is human error and the angles used to record the motion, or implementing the tracker's features to pinpoint the center of mass used to determine the distance traveled. In conclusion, through the lab, we discovered that the physics principles of Newton's second law and the momentum principle can be used to predict motion. However, it is subject to slight differences when not accounted for all factors.